All right, so now let's get into the inference procedures for comparing two means from two samples. When the true population standard deviations of both populations are known, if we know these sigmas here, right, then this test statistic, remember test statistic is always our estimate minus the parameter divided by the standard deviation of the estimate. So our estimate is this, the true parameter would be that, and this is our standard deviation of our estimate. If you have the true population standard deviations, then this is distributed normally. This has a z distribution, standard normal distribution, right? It's a z-score. However, when the population standard deviations are unknown, we use the standard error. We replace these unknown values with these known values, remember? And when we do that, if you recall, these introduce some extra error in our values, in the values of our test statistic, or in whatever whatever in the distribution we're talking about. So that extra error needs to be accounted for by the student's t, that t distribution made by Gossett. So when the true population standard deviations are unknown, then this test statistic, same thing, only I'm replacing the standard error on the bottom, has a t distribution with this many degrees of freedom. So you guys might be saying, well, whoa, that escalated quickly. Remember the degrees of freedom used to be n minus 1 for a single sample? Well, for two samples, it's kind of complicated. Well, it's really complicated, and I don't really know where this formula comes from. I know there was a paper, written by some guys a while back, but that's beyond my knowledge. But and the thing is, you could certainly, if you just look at it, it's, you're taking the standard deviations divided by the sample sizes, or variances, I guess, sample variances and square, whatever. Don't worry about this. You're not required, it's not even on the formula sheet. We're going to simply use technology to get this value. When you run a confidence interval or a hypothesis test, it will calculate this value for you. Okay, so we're going to use that. There is a way to, on the AP test, where you can estimate it using the smaller of your two sample sizes minus one, but I don't like that technique, and you lose some power when you do it, so we're just not going to do that. Let's just use our calculator. We have it, use it. The calculator will calculate this. I recommend that approach. All right, so a two sample t-interval for the difference in means is going to be, all intervals, confidence intervals, are your statistic or your estimate plus or minus a crit value times the standard deviation or standard error of the statistic. So that's going to be this. That's our estimate. T-crit, because it's a t distribution. This is the standard error of that estimate. Okay? And then this is that crazy degrees of freedom. So this is how we do a two-sample t-interval for the difference in means. All right, so like before, I have a worked out problem, so you don't have to listen to me and watch me write it all out. Let's just follow along and figure this out. Actually, I'm going to put this in my calculator so I can talk about a couple things. Hold on one sec. All right, for their semester 2 project, Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chips as the name brand on average. To investigate, they randomly selected 10 bags of Chips Ahoy cookies and 10 bags of Great Value cookies, and then randomly selected one cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each. Here are their results. Construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. Okay, so first of all, we should kind of just look at the data. Here's the data in the calculator. So here's the Chips Ahoy menu, plot properties, add an X variable 5, and here's the Great Value cookies. All right, well, that's interesting, I guess. If I were to just look at it informally, it looks like I would say the means are about the same. Looks like they're centered about the same spot. Maybe the great value is a little higher. Well, the biggest difference between these is the spread. Great value cookies have a lot of spread. They got some cookies with very little, not very many chocolate chips, and some with quite a bit. Whereas the Chips Ahoy were more consistent. Maybe they got better quality control. Who knows, right? All right, so here we go. So the P, the parameter, mu sub C is going to be the true mean number of chocolate chips per cookie for all Chips Ahoy cookies. Mu G is the true mean number of chocolate chip cookies for Great Value cookies, ditto. Conditions and assumptions. The bags and cookies were randomly selected for both samples. Notice I'm commenting on both samples being random. You must do that. 2, n equals 10 is less than 10% of all Chips Ahoy and Great Value cookies. Again, I'm referencing both. Normal, large sample. We got to check it for both. So both sample sizes are small. They're only 10. So we have to look at the distributions. We're looking for outliers and strong skewness. If we have outliers or strong skewness, we're going to fail this check. This is maybe kind of an outlier, but I don't think it really is. Might be easier to look at a box plot. Certainly easier to copy these on your paper. No outliers. This is skewed a little bit to the right, but not much, so I'm going to say we're good. I have to copy those graphs. I have to label them, and then I have to make a comment. Both sets of sample data are approximately symmetric with no outliers. Again, this is optional, or actually this is just not needed anymore, so don't say that. Name the test. This is a 2-sample t interval for the difference in means with this many degrees of freedom. Here I did note which way I did my subtraction. Here's my confidence interval. So these are both gotten through technology, and we really need to use technology now because that degrees of freedom formula is so complex. So here's how we do it. Go to the calculator page. We're going to do a confidence interval, stats, confidence interval. This is a 2-sample t interval because I don't have the population standard deviations. Do I have the data or do I have the statistics? Well, I got the raw data. I don't have the statistics. List 1. So this is where you decide which order you're going to put them in. I'm going to put the Chips Ahoy first and the Great Value second. Why? I always like to put the one that I think is bigger, like Chips Ahoy is the name brand. So I would kind of think they would have more chocolate chips than the Great Value. I don't think that's the case here, but that's why I did it that way. It doesn't matter which way you do it. You just have to make sure in your conclusion that you word it correctly. So I'm going to go Great Value. No, I'm not. Chips Ahoy minus Great Value. Frequencies, leave them alone. Confidence interval, 99% because this is important. Pooled, always no. We talked about this in class. Quickly, the pooled is a different test that gets you a little bit more, a little higher degrees of freedom, I think, and a little bit more power if you can make the assumption that the standard deviations of your two distributions, your two populations, are the same. I don't know why we can't make that assumption, so we're not going to. And also, if you look at these graphs, it really doesn't look like the standard deviations are the same either. So, long story short, in AP Stat, we're going to always answer no to this. So don't pool. Okay. The only time we pool is with proportions, and proportions are always pooled, so they don't even ask you to do it. They just automatically do it in the background. So if it ever asks you, no. And there's our confidence interval. There's our lower bound. There's our upper bound. And here's our degrees of freedom. So we have to copy that down, 13.145. Get that on your paper, and then put down your interval, negative 4.81 to 2.81. Conclusion. We are 99% confident that the interval from negative 4.8 to 2.8 chips captures the difference in the true mean number of chocolate chips in all Chips Ahoy cookies minus the true mean number of chips in all Great Value cookies. So I kind of put my difference, Chips Ahoy minus grade value. This doesn't sound right. I should be saying the mean number of chips per cookie in all Chips Ahoy cookies, and the true mean number of chips per cookie in all grade value cookies. For some reason, I didn't come up here and just copy this down like I should have. I was trying to cut corners. Now, would that cost me a point on the AP test? Probably not, but don't risk it, right? All right, so that's confidence intervals. Now we're going to do significance tests, and we will be done.